So now that you've built your Rube Goldberg machine and it works, you have to calculate kinetic energy, potential energy, and velocity. I know we worked on KE and PE earlier in the school year, but I wanted to make sure we remember how this goes. So let's remind ourselves, how do we calculate kinetic energy? So I've got the formula here. We've got kinetic energy equals 1/2 times the mass times velocity squared. Wait a minute. What does this velocity squared thing mean again? Remember that velocity squared means it's the velocity times the velocity, so that's not too bad. So we're going to put that over here in the corner so we remember what it is. But that brings me to a new question. What if we don't know the velocity? In all these examples I gave you in the beginning of the school year, I always told you what the velocity was. You never had to calculate it. So this brings up a new problem. What do we do with this thing called velocity? So velocity is the speed of something in a given direction. So speed is how fast you're going. Velocity is how fast you're going with a specific direction. So velocity is calculated by the distance over the time. So I'm going to put that in the corner right below kinetic energy so we can remind ourselves when we forget. So here's a practice example. A skier about halfway down a hill travels 2 meters in a half a second. So what is his velocity? So first we've got distance, or d. We're going to put that at the top of our equation. We've got t for time. We're going to put that at the bottom of our equation. And if we take 2 and we divide it by 0.5, we get a velocity of 4 meters per second. So I want to make sure you remember that you always have to do this in metric units. So no inches, no pounds, no feet, always in metric units. So here's one for you to try. So Hercules, that's my dog, chases a rabbit to the south, because we have speed with direction, for 6 meters in 3 seconds. What is his velocity? So go ahead and work that out. I'm going to wait for you. Okay, so let's see if you get the same answer that I do. So first, our distance here is 6 meters. Okay, so we put that at the top of our equation. We've got time, 3 seconds. Put that at the bottom of our equation. When we do 6 divided by 3, we get a velocity of 2 meters per second. Okay, so now we've understood velocity. It's just distance over time. So let's take this and translate that into kinetic energy. So I've got the kinetic energy for Hercules as he's chasing the rabbit. So I've got 0.5 times the mass. He's 68 kilograms. Remember, you have to use metric units. He's about 150 pounds. He's a very large dog. And then it's velocity squared. So we calculated our velocity to be 3 meters per second. So I have to do that twice. 3 times 3. You should get a kinetic energy of 306 joules. Remember, joules is our unit for kinetic energy. So kinetic energy, pretty easy. But let's talk about potential energy. So remember that potential energy is mass times the gravity times the height. And for the purposes of your calculations, we're going to use 10 meters per second squared, or 10 meters per second for gravity. So you need to use meters when you're taking these measurements for your later calculations in the Rube Goldberg machine that you're building. So convert those centimeters into meters. You can use a calculator online to do that. It's pretty easy. So I put our potential energy calculation over in the corner, and let's go back to a skier. How much gravitational potential energy does a 60 kilogram skier have at the top of a 20-meter hill? So we've got our mass, 60 kilograms, put that in the beginning. We've got our height of 20 meters. And then we've got 10 meters per second squared for gravity. So if we multiply those things all out, you should get a potential energy of 12,000 joules. Okay, so now it's your turn. How much gravitational potential energy does this 15-kilogram velociraptor have at the top of that 70-meter ravine? So I will wait while you calculate. Okay, so let's check your work. So first we've got our mass, 15-kilogram velociraptor at the top of a 70-meter, that's our h, goes at the end. And then we've got the 10 meters per second squared. You should come up with an answer of 10,500 joules. So what is this going to look like for your Rube Goldberg machine and the assignment? So you will need to calculate the kinetic energy or potential energy at every step. So you're going to measure all the distances in each step of your machine, which was the weeks before, the project you did the week before, and time each step as you go so you can determine the velocity. So if you know that you're using a marble rolling down a piece of wood, and that marble is traveling 1 meter and it took 2 seconds, you can use those things to calculate your velocity. That velocity is going to help you determine the kinetic energy or potential energy. So what do you need to submit to me? So for every step, you're going to calculate velocity. You need at least 8 steps, remember, for freshmen. Calculate velocity, calculate the gravitational potential energy, calculate kinetic energy, and list the forces in each step. Okay, so here's an example of what you're going to see in the document that I'm going to send to you. So you're going to describe the objects. So in the beginning, we have a ball at rest that's going to cause a toy to move. So the ball has a mass of 0.25 kilograms, and I'm starting the ball at 2 meters, and the toy is approximately 0.1 kilogram and also moves at 2 meters. So I don't expect you to have a way to get the mass of these objects. Google it and do your best to find an approximate weight for whatever mass, for whatever object you're using. In the document I'm going to send you, there'll be a sample of some common objects and their masses, but it should be pretty easy for you to get an approximate mass. You're going to have your gravity is always going to be 10 meters per second squared. So first we're going to calculate the velocity of the objects. So the velocity of the toy, because the toy is moving, it traveled 0.2 meters in 2 seconds, which gives us 0.1 meters per second. The ball is not yet moving, so it's at 0 meters per second. Potential energy. So the toy is going to hit the ball will fall. So the potential energy of the objects, which is the ball because it has the gravitational potential energy, we know that it's 0.25 kilograms times the 10 meters per second squared for gravity times the 2 meters that the ball is going to fall gives us 5 joules. So the kinetic energy of the objects, because it's the toy that's walking to hit the ball, it's 1/2 times the mass, so 0.5 times the very small mass of 0.1 kilograms times its velocity twice, so 0.1 times 0.1 gives us 0.001 joules. Very small. So in the second half of this step, you're going to use that potential energy that you calculated before to see how it changes. So now we have the ball falling. This is the second half of step 1. So again, the mass of the falling ball, mass hasn't changed, it's 0.25 kilograms. The height is now 0 because it's fallen to the ground. So the velocity of the fall, how long did it take it to fall 2 meters? It took 0.32 seconds, which gives us a velocity of 6.3 meters per second. So now we're going to calculate its potential energy. So we take the 0.25 kilograms, that's our weight, times 10 meters per second squared, times its height, It's at the ground, so its potential energy is 0, right? Because it's on the ground. But we can calculate its kinetic energy. So 0.5 times the mass times velocity squared gives us 5 joules. Great, because we had 5 joules of potential energy in step 1, A. Now we still have 5 joules of kinetic energy in step 1B. Again, remember the law of conservation of energy cannot be created or destroyed, just transformed into a new, transformed or transferred. So it's been transferred into a new object and we still have the same amount of energy. So that's what you need to do. I understand this one is pretty confusing. That's why we're going to have help sessions, and please reach out if you have any problems.